Hey folks, Michael Johnson here. Whoopsie, we got a wrong screen up. There we go. I think we're on the right screen, but I just want to make sure. I tell you, these technical difficulties. No, we got to check our stream health. I think we're doing good here, folks. Have we switched over? We've switched over. I don't see myself talking though. Is this right? I hope it's right. Let me give it a second to come in. I'm not moving though. That's a problem. You don't see me moving. I'm kind of frozen. So give me a second here to fix that. Back in a moment. Hold on, folks. We're fixing stuff. There's a problem with my. There we go. This thing wasn't running. Put this in the way. Put that in the way. Put that back. Now we should be good. We should be back in action, I hope. Technical difficulties. Thanks for tuning in, folks. We're going to just do another check. Yeah, audio looks good. Everything looks good. So, whoops, now we're showing what's gonna happen a bit later. So, hey, welcome to the Energy Sketch, folks. Good to see you. Good to have you here. Mute that. Yes, hello. So it's 2025, 0224, 24th of February, 2025, and we are live at 12:12 p.m. Eastern time for a little energy sketch today. I don't know if folks out there watch TikTok or whatnot. I don't really watch TikTok. But I go through phases possibly with like YouTube shorts. Sometimes there's like at the end of the day, just flop down and just be entertained. And there's sort of like a scrolling, scroll. So you see a lot of these shorts that come up. And of course, there's an algorithm behind that that's feeding you outrage. Which is a whole other topic, not really an energy related topic. Well, I mean, that's a personal energy related topic. And a lot of these shorts that seem to fall in my feed are things about, well, renewable energy possibly. And I kept coming across these clips, these short clips from Jordan Peterson talking about renewable energy. And there's a few threads there that I wanted to just explore. And I mean, I was a bit, I don't know, worried to like share this thing. I'm like, I'm going to cause outrage, but like, no, like, I don't know. Some of his messages we could get into, a little bit later, and we will get into it a little bit later. But I want to just debunk some of the sort of like overblown things that he gets into in some of these short clips. And keep in mind, like these are short clips, so I'm also guilty of like taking things out of context, perhaps, but they stand pretty much. From what I can see of the other stuff that he's shared out there on longer form podcasts and other videos and interviews and stuff like that, it's all in the same ballpark of stuff that he shares there, which is like essentially a message of like, what are you doing with this rush to renewables? It's just sort of like this urgency, this emergency, climate disasters, against that kind of a over dramatization perhaps of it. And there's elements of cost that come into the conversation also, which I think we can debunk, and we may debunk even further in future episodes. Not that I'm making any promises here. So, of course, quick disclaimer, right? I work in energy, which is a great thing, positive thing. I mean, I am blessed and so happy and to be working in an industry where that aligns with my social vision for the world and my skill set in engineering and science and math. I get to use that in service of like providing good quality energy to the world and working on all kinds of cool technologies. So, that being said, all opinions are my own. We're sketching stuff. We're riffing here today. So I hope you enjoy. Let's get into it. We're going to listen to Jordan Peterson now, a couple of little short videos.
They're not energy dense. They require tremendous infrastructure to produce. They might be renewable at the energy level, but they're not renewable at the raw materials level. So that's a complete bloody lie. They're insanely variable in their power production. And because of that, you have to have a backup system, and the backup system has to be reliable without variability. And that means if you have a renewable grid, you have to have a parallel fossil fuel or coal grid to back it up when the sun doesn't shine and the wind doesn't blow, which is unfortunately very, very frequently. And so again, and I'm not going to say there's no place for renewable energy like solar and wind, because maybe there are specific niche locales where those are useful. But the logical, what would you say, antidote to the problem of reliability, if we're concerned about carbon, but we're really not, would be to use nuclear. Is there not energy?
So much to unpack there, and I let it go all the way to the end, but I've extracted really the essential points that I want to get into a little bit later. But we're going to listen to another clip first. But I'll just go through essentially the. Okay, good. Checking the stream health, all good. They're not energy dense. They require tremendous infrastructure, right? There's a lot of these, like, just like, I don't know what the right word is there, just like throwing these words like tremendous or insanely. They're insanely variable in their power production. Because of that, you have to have a backup system. Yes, you do need a backup. Like, it's called storage. Like, people are aware of the need for energy storage, right? We have battery systems, we have hydrogen, we have all of the long duration energy storage. Like, hello, like a shitload of really smart and creative people are working on the problem of storage. So, right, of course, reliability without variability. Yes. So then this next point is just off. Like, it means if you have a renewable grid, you have to have a parallel fossil fuel or coal grid. Like, no, there is no parallel grid. There is one grid, and it has generators that are either fossil or renewable. But those things work together. And this is part of the super interesting challenges that we're up against right now as renewables scale, is how to manage the grid. There is only one grid. There is no parallel grid. We don't need to build a parallel energy grid to carry the energy from fossil while there's another grid that's carrying the energy from renewables. There is one grid. Sorry, I got a bit excited there. Again, this like overblown language, which is unfortunately very, very frequently, like, it's this like dark, menacing tone of like, solar doesn't shine very frequently. Yeah, so we're going to debunk all this in a moment, but we're going to get into one other video.
The
So let's have
sun
a
and the
listen.
wind are renewable, but that doesn't mean that solar and wind power are renewable. Those aren't the same thing. And the reason I'm saying that is because the lifespan of solar panels isn't very long, and the lifespan of wind generators isn't very long. And so they're not renewable at all, because once they exhaust themselves, they have to be scrapped and destroyed, and then they have to be rebuilt. So I don't understand what's renewable about that at all. Like, if we were growing solar panels in a field, that would be a different thing, but we're not. Wood is renewable because wood will grow. This
Okay, so we're going to minimize this. We're going to maximize this now. We're going to get into the debunking phase. But let's just summarize a little bit. The sun and the wind are renewable. That doesn't mean solar and wind power are. Those aren't the same thing. Yeah, they're not the same thing. And actually, I went into the Oxford English Dictionary recently, and but I don't have that with me right now. But we could get into the definition of that. What is the definition of renewable? Something that renews, that regenerates itself on its own. Yeah, of course, we don't grow solar panels in a field. We make solar panels from metals, silicon panels, and glass mostly. I mean, there's frames made of steel, maybe aluminum, there's glass, and there's silicon, and there's electronics and the cabling and all that stuff. That's what makes up a solar panel. And a wind turbine is mostly like a big ass tower made of steel, along with the machinery, the generators, the gears inside, the cabling, and also the blades, which are made typically from like carbon fiber, not carbon fiber, but fiberglass, let's say, reinforced, fiberglass material. And so it's kind of a bit of like overblown language. Like, we're not growing solar panels in a field, therefore they are bad, right? They need to be scrapped, destroyed, and then rebuilt. Like, yes, this equipment has a lifetime, And there are a shitload of really smart and brilliant people that are working on minimizing the impacts and making it so that this equipment is as recyclable as possible, right? This is a societal wide transformation that's happening right now in all sorts of things, making things circular, right? We need to move towards circular economy. And actually, well, the sun and the wind are renewable. Let's just start there. We're going to just jump into it. Let's say, is the sun renewable? Actually, no, it's not, right? The sun, this is we're going way deep in here. The sun, right? Let's draw a sun here. This is the sun. Inside the sun, there is fusion nuclear reactions happening in the sun, right? And it's producing energy. There's energy coming out of the sun in the form of radiation over a wide spectrum of radiation, right? So actually, the sun is a non-renewable resource. I will share that with you now, right? The sun has a given mass. There's a mass of the sun, and actually there's a rate of change of the mass of the sun, which is approximately 4 million tons per second. And I got this from, well, I checked it on ChatGPT and on Wikipedia and on some other astrophysics websites. But also, is that right? Because I got that number also from a podcast of of Elon Musk, which is kind of funny to see. I mean, Elon Musk is so bullish on like solar energy, right? It's incredible. Oh boy, I don't have the data in my little thing here. Anyway, this is again, we're riffing here. There is a certain rate of change of the mass of the sun. So actually, the sun's lifetime, right? The sun's lifetime is only a few more billion years. So it's going to last for our lifetime and probably most of our descendants. But after a few billion years, like the sun is going to undergo some pretty profound transformations and is going to transition into like a white dwarf or something like this, and it's going to expand, and the whole dynamics of like the mix between the internal fusion reactions and the external like gravity is going to completely change. But yeah, the sun is non-renewable actually, but on the time scale of like our lifetime, it is renewable in the sense that it comes up, as the earth turns, the sun comes up and goes down, comes up and goes down every single day, the same thing. So um, yeah, so the sun is actually a non-renewable resource, and it's the sun that drives the wind. So wind power is really just solar power that's been converted into kinetic energy of the air on planet Earth. Yeah, so that was our little rant on this. So we're just going to move this stuff out of the way. Move that down there. That's cool. So that's what we were talking about here. The sun and the wind are renewable. Well, technically not. Right. But then this thing about solar and wind power, like it's not that those panels are renewable, like they grow themselves. I mean, there's a recyclability here, which is a key concept. The recyclability of wind power equipment, let's say, the equipment, right, and solar also. I mean, let's talk solar. It's like a frame that's made out of like aluminum. Aluminum is eminently recyclable. The great recyclability of aluminum. Aluminum cans, can be remelted and made into new cans. There's a robust economy of remelting, recycling of aluminum. So what else is in there? Aluminum, maybe steel, for the frame material. Then there's like glass, and then there's like the polysilicon, let's say, stuff, the actual panels, which are like a tiny portion, I would think, of the mass of these things. And see my previous videos on actually some investigations into a new way of using microwaves to bombard pieces of solar panel in order to heat up the films on them and make those easier to peel off and then recycle them. So again, like there are challenges, there are issues today with that. But I am personally, yeah, optimistic, and I believe in continuous evolution. And if the right incentives are, put in place for this stuff to happen, then there's going to be scaling of this. So that's for solar. For wind, equivalently, right? You've got a big tower and you've got your blades. So this is mostly steel, and this is like, let's say, fiberglass, something like that. So yeah, I mean, there's some bad looking images available on the internet of like graveyards of wind turbine blades that are being landfilled or being ground up to burn and to provide heat, which is maybe an interesting avenue, but there's other issues there. But even our company, Siemens Energy, and others have released recently recyclable wind turbine blades. So again, it's a question of, I guess, carrots and sticks. I mean, we could talk about recyclability for materials of everything that we make. Uh, Talk about cell phones. I mean, cell phones, electronic waste. I mean, there are terrible stories of like these mountains of e-waste that gets sent to, third world countries for somebody to sort of ply at them with a blowtorch and just like nasty chemicals. It's like awful. There's awful stuff happening in those industries, that we as government and society, we have power there, but due to whatever factors, it's complicated to regulate and all that stuff. But this is the job of us as society to regulate, to put in place the right conditions, economic and other incentives, so that this materials and these things are well managed. And that applies equally well to this equipment. So I'm not against. No, what am I trying to say here? This stuff can be recycled. Okay, wind power equipment, solar power equipment can be recycled and can be made anew. Yes, I mean, let's say that the lifetime is maybe what, I don't know, 20 to 30 years. It's kind of the same thing with fossil. I mean, you build a big power plant, it needs to be refreshed also. Parts need to be replaced. The same thing. You look at any publication around, fossil power generation, it's going to be roughly in the same type of lifespan of that equipment. So chemical processing equipment, all this stuff. I mean, it's dealing with high pressures, corrosive materials. All that equipment equally well has a limited lifetime and needs to be scrapped, destroyed, rebuilt, whatever it is. Ideally, not scrapped and destroyed, right? Fossil also needs to be refreshed, renewed, refurbished, recycled. There's a circularity there. There's like, you build a bunch of equipment, you build all this equipment, you operate it, you build, operate, and then at the end of the lifetime, you ideally you take the equipment, you disassemble it, and you bring some of it back here. This, circularity. It's not a new concept, but it takes, real guts, I guess, politically and economically and socially and technically to realize that. So that's the spiel about recyclability of that. Let's just put some check marks here. We talked about this. We talked about the lifetime. This, we're not even going to go there. Wood, like wood is renewable. Okay, you want to talk about wood? Let's not talk about wood today. We're gonna keep this, and we're gonna move this down over here. Um, gonna move this. Note to self: I need a better way to manage this stuff, but that's okay. We're having fun. Well, let's talk about wood. Um, if you were to graph actually like, let's say, energy consumption of the world, right? From way, 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 way back. I don't know. I don't want to put a number here, but let's say this is, I don't know, 1600 or something. Like, we had always like a little bit of Wood, 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 wood. This was wood here. Biomass, wood. Right. Then at some point, let's not even put a year here. I don't want to embarrass myself. Right. At some point, like we discovered coal power. So like boom, like coal came up, right? And then boom, like oil, boom, like natural gas, right? And now we're kind of like, now we're seeing these little like renewables is like creeping in. Like there's a little tiny sliver of like, we're now in the adolescence of renewables. It's in the 12%, 10%, 12% ish, right? And these things go rapidly, like, right? Like this scales is exponential. So we can expect that, this is going to scale up rapidly. And we'll get into maybe the next sketch, we're going to get into an article that was blew my mind about the expected cost decreases based on the last 20 to 30 years of solar and wind power technology and the implications that that has for if we make the energy transition to renewables faster, it will be cheaper for society because we will more rapidly realize the cost reduction gains that are possible for us to realize as we go down the learning curve. So let's just remember that things go exponential. So even if there's people on the internet that are going to tell you like renewables, it's only 10%, it's only 8%. Yeah, that's kind of like someone saying like COVID, like, there's just a few cases. And then like a month later, like there's thousands and thousands of people dying, right? Like we as humans have a very bad sense of exponential growth. So keep that in mind whenever someone says, it'll never scale up. It's only 10%. Like, yeah, 10% compounded at an annual rate of return of whatever, 20%, 30% will rapidly boom and explode. And we want this. This is a good thing. And I'll get into all the details. Here I go, promising on another sketch that we'll get into the details of that, but we will. Exponential growth. Humans are very bad at understanding economic growth. And there was one example of this I remember. I think it was David Suzuki that gave this example of you have a little bacteria in a big lake, okay, or in a test tube. Imagine you have a test tube and you drop in a little bit of bacteria that doubles once a day, right? So you start with one molecule of bacteria, it goes to 2, to 4, to 8, 16, 32, 64, 28, 56, right? And if you want to have a few little tricks to remember. 2 to the 6 is 64. 2 to the 10 is 1024. Anyway, it's fun to remember binary exponents that way. But this test tube, right? If you imagine that you come back you let this thing go and grow for a long time, and at some point it reaches half, right? But the question is, how long will it take if this bacteria doubles its population once every day? How long will it take to go from half full to full? And people get this completely wrong because you think, oh, it took so long. It took years for it to grow from one molecule to filling half of the test tube. And it only takes 1 day for it to double and to consume the rest of the test tube to go from half to full. Like this is the power of exponential growth. And there's various other things like that. The the bet of if you had a chessboard and you start with 1 penny here, 1 grain of rice, right? You go here, here, here. How many grains of rice would you have by the end of the chessboard? And the chessboard is what, 12 by 12, so 144. So it's 2 to the 144th power is just like a number that's beyond comprehension, right? Like so big. So humans are very bad at understanding exponential growth. Hey, Mohammed, nice to see you. Thanks for stopping in. So this is me riffing here, and that's what we get up to. So we're gonna try this again. We're gonna do the next part here. There we go. So we talked about what were we talking about? All this stuff about lifespan, about scrapping and rebuilding and recycling. Okay, let's get into some other stuff here. The density, right? Jordan Peterson's thing there was they're not energy dense. Well, hold on, like technically, like we're not talking about the same thing. So there's two different things that we need to talk about here. Energy density is more related to like a fuel. Okay, this would be like related to a fuel. Let's say if I had a bowl, if I had this cup full of fossil fuel, full of a liquid hydrocarbon, how much energy would be contained in there? So this is an energy per volume. That's what we would call an energy density of a fuel typically. So that could be in like megawatt hours per cubic meter or megajoules like per liter, any other metric like that. What we're talking about with renewables is different. So it's not energy here. We want to talk about the power density, which is a different metric. Okay, which is a different metric, which is going to be for like a generator, a power generator, which would be more in power per unit area. Okay, we would call that like kilowatts per square meter, for example. So that's the idea. Like if you had a plot of land here and you put up if you put up wind turbines, you've got to space them out, right? Wind turbines need to be spaced out um, in space because you don't want the wakes from one of the turbines has impacts on the other turbines, so they need to be spaced out. Or if you filled this area with, here's a little sketch of, this is a solar panel, this is another solar panel, right? This is what we're talking about more about power density. And right, this is again like this is just there's no nuance here. They're not energy dense. Like first of all, we need to talk about power density when we're talking about generators because that's the metric that's appropriate. Like how much land area do I need to spread my solar panels over in order to produce the amount of power that I want for my load. Let's say I have a small city or a village and I want to build next to it a large solar farm and wind farm that's going to harvest all of the bountiful energy that's coming from the sun, the beautiful sun that's going to die in billions of years. Like it's so sad. Like anyway, we already talked about that. So the beautiful sun that is bestowing its nuclear fission generated radiation onto us every single day and creating the balance of the heat on different sides of the earth that is causing the wind to turn around when mixing with the rotation of the earth. So it's about power density here in kilowatts per meter squared. And this thing about it's not, like if anyone tells you that, like I would always question that. Like, okay, what's, there's a scale here, right? Like it starts at 0 and it goes to, where does it go to? I don't know. Where's the line? Like when do you say it's not versus it is? Like there's no line here, right? So if we wanted to have a real conversation about this, we would really get into the details and we would, for example, here's what we would do. I'm going to show you a little open source website. Oh my God, where's my websites? Did I lose my websites? I lost my website. Oh, model.energy. Yeah, we're gonna make this big here, and we're gonna jump into a whole other little topic here to show you that you can go and build your own zero emission electricity supply on this website called model.energy. And this stuff is open source, beautiful open source energy analysis tools coming out of a particular package called PIPESA. Here we go. This is PIPESA, Python for Power System Analysis. So this website here, model.energy, go check it out. What you can do is find your location on the Earth, and I chose a Canadian Alberta location, perhaps intentionally, because that's probably the best place in the country to put solar power here in the south of Alberta. The insolation there, the kilowatt hours potential from solar is highest here. So you can select your point on the map, scroll down a little bit. There's some options here. It has weather data, only these years. There's, until we get a bigger hard drive. If you want to support model.energy, there's probably a donation box somewhere. You can support these guys at Open Energy Transition, Tom Brown at TU Berlin, doing beautiful tools here. There's a whole suite of tools here. So there's a thing about distribution. Then you click this button, fetch wind and solar, and it's going to fetch the energy data at that position the wind and solar potential power of hypothetical 1 megawatt generator. So you could install a hypothetical maximum 1 megawatt generator of wind, which would be a certain area, and you would need more area as you go further north or whatever. There's some details there, but what this thing does is it gathers all of the weather data and then shows you how your little model energy system would actually operate in terms of wind and solar. So solar is the yellow, and it's got the whole year here, and you can zoom into different parts of the year. But you can see, like, already we can see some interesting trends. The darker color here, this dark gray, let's say, call it, is the wind potential, and the yellow here is the solar potential. So you can see there's a bit less wind in the summer, more wind in the winter, which is interesting because, right, in the north, often we're heating with electricity. In Quebec, for example, we heat a lot with electricity, and this causes additional peak loads in the winter when we have these very, very cold days. But luckily, the wind is there for us, providing additional energy in the winter, and sun provides more in the summer. Like, isn't that lovely? But we're getting a bit off topic. We're talking already about the variability, but let's go and just show you a little bit of some issues around the variability of this little system here. What's interesting to note is also that here's the sun, right? This is midday. The sun's coming up, going down, coming up, going down, coming up. This is one day at a time here. The 5th, June the 6th, 7th, 8th, 9th. And what's interesting is, sometimes the sun is high, it's low, cloud cover's not really maybe accounted for, but I think they probably measured the weather data here to come up with this. But often what happens also is that sun and wind are actually very nicely complementary in most locations. And you can see here, the sun comes up during midday, and then in the night, the wind comes up. And that's because, again, the wind is only solar energy that has been collected on the surface of the Earth. The sun is heating one side of the Earth differentially from the other side. So as we go from day to night, we sort of pass through that transition area when the wind starts to pick up, typically. So you can see here, boom, like there's a windy day, a windy night actually here. So balancing the sun and the wind is, people do this. Like this stuff is a kind of a toy model, but there are very, very advanced energy system models. People are doing this types of analysis. There are a whole boatload of really smart people that are out there solving the problem of variability in renewable energy systems. So, like, this is not a new issue. It's not a new phenomenon. It's not a new problem. Let's get back to where we were. We were talking about power density. Yeah. So, we went into the variability here. Say this is, we kind of went down this road a little bit already. They're insanely variable, like this sort of like doom type of language. Like, they're insanely variable. Don't touch them. They're so dangerously variable. We can't handle it. Like, hello, batteries. Hello, long duration energy storage. We have all types of long duration energy storage systems that are already exist. Pumped hydro, for example. If you have two reservoirs of water, you pump the water up when you have excess energy, and you want to store it. You pump water up to a higher reservoir, and when you need the energy, you open the floodgates, the water flows down, and you make power. Like, that exists already at scale. Of course, it depends on having a certain geology in your location, so it's maybe only appropriate in certain other locations. But there are 1,001 other types of long duration energy storage technologies, and I've spoken about two of them that I am extremely bullish on. All opinions are my own. Metal fuels, right? Iron, aluminum, storing excess renewable energy in the form of metals that can be stockpiled and stored in grain silos. This is one of the brilliant, beautiful, amazing, and awesome innovations that's coming down the pipeline. If only we could sort of get rid of this, like, BS, like, shut it down, it'll never work, negativism around the energy transition and renewables. Then we could really get on with scaling up stuff that's going to really make a difference at scale for society. We're getting excited here. So let's put this here. and let's get back to it. So we talked about the energy density, and that actually, no, you don't want to talk about energy density. We want to talk about power density, and that's related to the land area that you would need. And there's crazy other stuff like, right, we there's this other side also when people say like we don't have enough land, like it's gonna impact food production, like agri-solar. Let me tell you about agri-solar. This is crazy. This is so cool. Like, right, the problem, potential problem is that we're going to cover all the land with solar panels. We're not going to have anywhere to grow our food. Right. Okay. This could be a problem if we were, I don't know, silly enough. Well, if the incentives and the system was set up in a bad way to make that possible, like that could be bad. Yeah. I mean, we don't want to use cover over like our good agricultural land. We don't want to cover it over with suburban sprawl either, but we do that, unfortunately, sadly. I mean, wind is less of a problem. You just need some access roads, and the wind turbines can happily coexist with agriculture, and that can potentially bring in additional income streams for our dear farmers who are, being stretched and whatnot. But there's this concept of agri-solar. So, right, instead of this is the ground, this is the ground. Let's put the ground here. Instead of just building like a shallow thing here with solar, and you gotta flatten the ground, cut everything. Like we see around the internet, there's some memes, there's some bad images that show like a nice field that's been just raised and flattened to have solar panels on it. I agree, that's not very nice. But what we can do is actually make them higher and put them maybe vertically or this. And actually, when we have the sun shining here, right, it provides shade. There's now shade here, and boom, like actually certain crops like thrive in the shade actually. And I was just looking up a paper here. Most importantly, many studies on a wide variety of food crops have now demonstrated that agrivoltaics increases crop yield, which include basil, broccoli, celery, peppers, corn, lettuce, grass, potatoes, salad, spinach, tomatoes, wheat. Great things, right? Great things we can grow underneath solar panels, uh, unlocking new lands where we can put solar panels without disturbing the agricultural lands underneath, new income streams for farmers. And you can even, have, there's other things where you have sheep grazing basically here, right? This is a little sheep grazing the weeds. All this stuff is possible. There are beautiful, beautiful synergies that are possible with this. So that was a little rant there about agri-solar related to the density, the power density, the energy density, which is the wrong metric for solar and wind generators. It's power density, required land area. But remember, there are ways around that, such as agri-solar. Okay, let's get into it. Let's keep going here. Again, this language of like the tremendous infrastructure. What does it mean, tremendous? Right, tremendous. And there is a rigorous scientific discipline here that's called LCA, life cycle analysis. Okay. So here's what this life cycle analysis does. Let's take the example of a wind turbine. It has a lifetime, let's say 20 years lifetime. It produces a certain amount of energy per year, let's call it, a certain amount of megawatt hours of electrical energy is produced. But there's a life cycle of this thing over time, right? If we let's say this is time marching forward, and you need to like do construction, you need to construct it, you need to operate it, you need to, what's the word I'm looking for? decommission, 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 right? And each of these has like inputs in terms of energy, associated emissions, associated pollution, right? This is a very, very rigorous scientific discipline called life cycle analysis, which will add up all the impacts over the entire life cycle from birth to death of this equipment, including all the embedded energy that's in and emissions that were used to produce the material that goes into the construction of it. Everything is accounted for in this life cycle assessment, and I've supported some life cycle assessments that have been done by some of the students at McGill that we worked on with the aluminum thing, right? So this is a scientific discipline that is very rigorous, that is around the world. And so again, like tremendous, like what's the number? What is the number that we should use there? And actually, like fossil fuels also requires tremendous infrastructure that has its own impacts and its own life cycle. So yeah, it's just right. Of course, these videos from these people is often just clickbait, meant to feed the algorithm, meant to just cause outrage. There's a lack of nuance there, a lack of subtlety, a lack of understanding, both technical, economic, social, all these things. It's just rants. And, well, I mean, I like to rant also, but I hope I'm opening your eyes to the fact that this is just like blah, blah, blah. Just tremendous infrastructure. Oh, it's tremendous, tremendous. Like, hold on. We can measure that robustly, and we can show that wind and solar actually have very low life cycle emissions and impacts, and we can situate those relative to other infrastructures, and we can pinpoint the elements that have the most impact, and we can work on instituting economic and technical incentives and support early stage research and help to scale up that new research into actual commercialization to reduce the impacts of those things. This is what we do in energy innovation, R&D development, and life cycle analysis. So, right, again, if it's tremendous infrastructure, yeah, okay, let's get into it. You really want to get into the details of how much infrastructure and what the impacts are? Sure, let's do it. But don't tell me that I should be against renewable energy because of the tremendous infrastructure impacts that it has. Quantify tremendous in a rigorous way relative to other things in a storyline that people can, that can resonate for people, that they can understand, that they can make sense of also. So maybe we'll get into that in future episodes, but we're having too much fun here. So we talked about this, we talked about that. Again, they're insanely variable in their power production. Yes, sun goes up, sun goes down. Well, it doesn't really go up or down. Earth turns, the sun looks like it's coming up and looks like it's going down to you, to us, as we're sitting on, the top, the outer skin of this incredible planet that's floating through space, that's receiving this massive radiation energy from the Earth, protected by certain wavelengths, are protected for us by the beautiful atmosphere and all of this stuff. But yes, they are variable. Like, okay, storage, like the way that we address the variability of renewables is with storage. And we do that at different time scales. And well, yeah, now this brings me, this getting excited here. There's a book called, Monetizing Energy Storage, a great book, Monetizing Energy Storage, that has this graph, which plots for us. I'm going to move this up a little bit because you probably can't see this. Make it a bit bigger. There we go. This book here plots for us a few different things. Number of cycles. So you can think about like, well, let's just plot something like what we plotted before, okay? Here the sun goes up, sun goes down. Sun goes up, sun goes down. If we only had solar energy, right? This is the energy that we can harvest from the sun. But oh no, like what do we do at night? Oh, what do we do at night? Like, well, what you do, what you do is, well, we haven't actually shown that. Let's say that this, well, if this was my demand, let's call that demand, DMD, right here, then I got a problem, right? I need to fill in the gap with something else. And typically this might be like fossil today. Like this is actually a good way to decarbonize and actually reduce costs is to go from, instead of having 100% of this generation as fossil, I install some solar and then I run my fossil less often. And I actually reduce costs overall in the life cycle. I probably need to invest more upfront because of the capital costs of the solar installation, but this is a whole other can of worms that we won't get into right now. But this is what I would do early on. But then what we can do actually is start to actually scale up the solar, right? If our solar was actually these two big humps, then here I don't need to run my fossil generator at all. I have this extra energy that I can then put into a battery and then use it here. So I'm able to kind of smooth out, right? This is stored energy that I use here. So what we want to do is overbuild the solar and wind, which addresses in itself actually the variability problem, because you would also have wind, as I showed, would come up in the night, which we're not showing there, but we're just doing a simple example here of only solar generation. So overbuilding the solar generation then gives us superpower. This is a superpower that we then put into a battery and use later at night. So at different time scales, you need it from like milliseconds to seconds to hours to days to weeks to seasons. So, right, we need storage. Yes, Jordan, we need storage. Like, I think everybody is aware that solar and wind are variable. This is a problem, and it's a problem to which we have a multitude of solutions already, and a boatload of solutions that are being innovated right now. So this we would call the frequency of discharge. So high frequency discharge, and typically it's like a graph like this. This is the space where we want to play. So high frequency discharge goes very rapidly. And this is to like modulate the frequency of the grid, stuff like that. And then there's like lower and lower frequency. This would be like, let's say this is in the hours in here. This is like days here. This is like, seasons is kind of here. Very low frequency. So, like once a year, maybe. I mean, we will need some kind of chemical energy storage that will be able to store significant amounts of energy for those doldrum periods when the wind doesn't blow, the sun doesn't shine, it's cloudy and dark in the winter, and we need power. Like, we will need this, and there are brilliant and beautiful innovative solutions to this problem, including metal fuels. um, I think this is wrong though. I've gone and screwed up. Uh, no, this should be time, delta time, I think. Delta time and frequency. So the high delta time, time of discharge, like high time of discharge, how long you need to discharge this. Here we're just discharging for a few hours. Um, I'm sorry, I've gone and screwed up this graph, but essentially, like chemical storage is here. There's kind of like let's say chemical storage. This is like pumped hydro. We could have like different types of batteries here, and we could have like supercapacitors or something like that here. Maybe we'll get into this book and this paper sometime later in another episode. But there's a really nice graph here that shows the plethora of technologies that exist today, commercially available, to give you reliability without variability. Like, we know the solution to these problems, and there are a boatload of brilliant people that are working on it right now. Thanks very much. We don't need your negativity. We need positivity here. Thank you very much. I mean, we need positivity, negativity. I don't know. We need nuance. We need positivity. I mean, I think there's enough negativity around the world, but we need sort of balance. Well, balance. Anyway, a topic for another day. Variability, again, insanely not tremendous. These are words that should throw up red flags if anyone justifies why we should or should not do something by using some non-measured names and words like that. Red flags. Yes. Okay. Now, this whole thing about the parallel fossil fuel grid, There is one grid. Let's just draw a grid. Here's what is a grid? Okay, a grid. Let's talk about a grid. Um, this really, we're gonna put a bunch of dots here. Boom, boom. No, we're gonna just okay. Here's what we're gonna do. Boom, 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 boom. There we go. Those are our little grid, our little things, and these things are all connected together. Boom, 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 boom. Right? Maybe these are like far away, so they're only connected by one thing. There's maybe a central hub here, like this. Okay, this is a grid. Let's call it a grid. And this is the way that Python for power system analysis, again, PIPESA, as we call it, Python for power system analysis. These are links. We call these links. These could be sort of generators. This is the way that we describe energy grids around the world. There are a boatload of brilliant people working on the problem of how to integrate renewable energy into the existing grid. And there are lots of issues. There are lots of improvements that we need to make. Our grid is vétuste, as I would say in French. It's, needs love. It needs some love a lot. But yeah, let's just say, right, this is how you would model a grid, and this could be like these could be generators, or this could be like a demand center. Demand center. So this imagine this is like a city, and you have a solar farm out there, you have a wind farm, and you have a fossil fuel plant. All of these three things, imagine these are our nice little links here. These are our pylons, our grid of different voltages and different capacities. And there's some DC, there's some AC, there's some buses, there's interconnectors, there's transformers. There's a shitload of fascinating equipment that is on the grid. Control systems of how to integrate, right, these new types of generators, right? We're used to, right, the grid was built a century ago, maybe more, early days, and the electricity landscape was significantly different in those times, right? It was much more about centralized fossil fuel plants that would feed directly to the demand centers. So now we're trying to take that infrastructure and modify it, upgrade it, play with it and make changes to it so that we can integrate these new variable resources like solar and wind. And this is a big challenge. And there are a shit ton of people, boatloads of people. Sorry, you can't see what I'm sketching here. And let me get this out of the way. Boatloads of very brilliant people that are working on this problem, but there is no parallel grid. Like, this is kind of a fear mongering. We need a parallel fossil fuel grid to back it up. The message there is kind of like, why bother making renewables when we'll need to build double anyways? We don't need to build double. There is one grid. It is vulnerable right now. We need to make improvements to it, and it could be made much more robust with those improvements, and we can much more rapidly integrate the variable renewable resources, which will reduce energy costs for society. We'll get into that in another episode, but there we go. So no, there is no parallel grid. Again, so to back it up, no, we have storage, and we do have today. Fossil is now transitioning into a mode where it's backing up renewables. So, right, in the old days, the fossil plant would run 8,000 hours a year. Now that same plant needs to have some modifications to it so that it can ramp up and down much more rapidly to fill in the gaps when the solar and wind are not running. Like, we do this today. We're doing this. This is what we are doing now today. And it's a good thing because that will reduce total costs for society, decarbonize our energy system. All of those are good things. And there are boatloads of brilliant people working on this thing. So bravo to all the brilliant people working on grid robustness and integration of renewables. Again, right? sun doesn't shine and the wind doesn't blow, which is unfortunately very, very frequently. This is again very, very frequent, insanely tremendous. Like, okay, let's get into this, and maybe we're getting to the end of the sketch. The time is flowing, time is moving. We're gonna. Whew, this is fun here. Control C, Control V. I need a better way. I need like a hotkey or something like this. So let's get into this very, very frequently that the sun doesn't shine and the wind doesn't blow. There's a thing called capacity factor. This would be the technical term for that, capacity factor. And if we go back to that wind example here it is. Capacity factor onshore wind, 33%. Capacity factor solar PV, 16%. That essentially means that over the entire year, right? Right. We had a hypothetical 1 meg. Whoopsie. We had. I'm trying to use two tools at the same time. Don't do that. We had a hypothetical 1 megawatt generator capacity of the solar and the wind. What this means, the capacity factor. Let's say hypothetical. If you had a 1 megawatt hypothetical maximum power generation thing. You multiplied by 8760. It's kind of weird that I know these numbers off the top of my head. That's the total number of hours in a year. That's 24 times 365. Okay, you could theoretically generate 8760 megawatt hours of energy. That's a power times a time duration. Power times time equals energy. That's the theoretical maximum that you could deliver in an entire year. So when we say that the capacity factor was approximately 30% for the wind, that means we take this times 0.3 and we get something like whatever, 2,600, let's call it, 2,600 megawatt hours from our wind power facility. Okay, right? So you could, I mean, maybe that looks a bit depressing. Oh boy, like 30%. Oof, that seems pretty low. Like, well, it is what it is. And it depends on location. And of course, there are some locations with really awesome wind capacity factors, like offshore Chile, that wind's just super steady, not too high, not too low, super steady wind. And you can just see there's a huge, amazing business case for wind in that region. North Sea, I don't know, offshore northeastern United States, probably also, right? There are certain locales that have super awesome high capacity factors. So build lots of wind in those regions. Like it makes sense. But, very, very, unfortunately, very, very frequently, like, no, again, there's no nuance there. I mean, yes, there's a capacity factor. It's less than 100 because typically, like a fossil plant, if it's fueled the entire year, it's going to run happily almost the entire year with a few maintenance outages here and there, depending on how long it's been operating, right? So the uptime, the capacity factor for a fossil fuel power plant can be, tremendously high. But again, it's related to the issue of storage and variability. So yes, renewable energy is variable. There's different capacity factors on it depending on where you are in the world, depending on the local weather potential and weather conditions. And yes, it is variable, and we have storage. We have batteries, supercapacitors, hydrogen, metal fuels, all of these amazing tons of other technologies, pumped hydro, flow batteries. We could get into that for many, many, many other episodes. We have the technology to deal with the variability of renewables. And I think next energy sketch, we're going to get into the economics of this, and we're going to share a paper that blew my mind, and I hope I can blow your mind also. That's going to show basically that if we go faster, we can make it cheaper for society to transition to a fully carbon-free energy system. So that was my goodness, folks. Thanks for tuning in. And well, this has been Energy Sketch Live, a bit of a rant, a bit of a flow. Thank you so much for tuning in, and have a great week, folks. It's been fun, and see you later. Toodles. I hope this works. Oh no, it didn't work. I got to go back to my